The current lags behind 90 degree with respect to the voltage. Phase means to say the one which gives the direction and supposed to be a vector quantity. Position offered by an inductor having certain inductance to the alternating current which is passing through it is called as a inductive reactance. Hello everyone, I am Vrinda, Faculty of Physics from Vidhyaashram Pre-University College, Mysuru, welcoming you all to session 3 of chapter 7, Alternating Current. So in today's class, we are going to deal with the phasors as well as the alternating voltage applied to an inductor as well as its phasor diagram and waveform diagram with respect to the inductive reactance. So in the last previous class, we had studied about the applied voltage to a resistor. So in today's class, we are going to study about the inductor. So first of all, what is meant by phasors? In last class itself, you had drawn a phasor diagram for the applied voltage to a resistor. In that case, you had drawn a phasor diagram which gives the phase. Phase means to say the one which gives the direction and supposed to be a vector quantity. So it is a vector which rotates about the origin in anti-clockwise direction. It rotates in the anti-clockwise direction, okay, with an angular speed of omega. Okay, the angular speed is represented in terms of omega. So the thing is, like, you have got your axis over here. Whenever you take the rotation, you take in this manner, that is anti-clockwise direction. It is anti-clockwise direction. So always a phase is the one which is called as a vector which rotates about the origin, and that rotation is given in terms of a vector. It gives the direction, which means to say it is a vector quantity. Next is, its magnitude represents the peak value or amplitude of sinusoidal wave. So sine wave, as you had studied, this wave is a sine wave. And the peak value, this is said to be V0, or else it can also be called as I0. So the peak value is said to be the amplitude or a peak value. This represents the magnitude of this phasor. Okay, so that is all about your phasor, what you have to know. Next, we are coming on to inductor. What is meant by inductor? Inductor is the one, it is also called as a coil, choke or a reactor, and it is a passive component. It comes under the example of a passive component because it stores energy. Okay, it stores energy. It behaves like a resistance when the resistor is connected to the DC circuit. Similar way, the inductor, when it is connected to a AC circuit, it behaves as same as that of the resistor. Okay, so next you can see that alternating voltage applied to an inductor, for which you are considering a circuit diagram to which inductor is represented. The diagram, that is a spiral helical structure over here, gives the inductor symbol, and next you're taking the AC source and then you're closing the circuit over here. Okay, so this is the inductor which is termed as L. L means you're speaking about the inductor, R is resistor and C means capacitor. Okay, so now this is the symbol, that is a coiled kind of a structure. This is the symbol of a inductor which is given in terms of L. So now our duty is to check when the alternating voltage is applied to an inductor, how exactly it varies with respect to current is the one what we have to see. Always voltage and current, we just look through each other and then give the conclusion, for which we have to consider, we know that V is equal to V0 sine omega t equation. We already know this, where V0 is the peak value, V is the instantaneous value, and omega t is said to be the phase value in case of the sinusoidal wave. Okay, so now since we know that, that is if di by dt is, that is the current, change in current with respect to time, then we just have an equation EMF is equal to minus L into di by dt. EMF is equal to minus L into di by dt. This equation we have got by using Faraday's law, and negative is due to the Lenz's law, what we had studied in chapter 6, electromagnetic induction. And since there is no resistance over here, what we do in the sense we consider KVL, Kirchhoff's voltage law, which gives the voltage plus EMF is equal to 0 according to Kirchhoff's voltage law. Now, on application of the value, substitute equation 1 and equation 2 over these values. This value, so it is V0 sine omega t minus L into di by dt is equal to 0. So what do we do in the sense, we just consider this as V0 sine omega t is equal to L into di divided by dt. Take your dt up, L down, so di is equal to V0 sine omega t into dt divided by L. Now, this is the current, that is change in current value is this one within this circuit, that is one part of the circuit. We need to know over the complete circuit what exactly is the current over here for the voltage what is applied. So for that we have to integrate it. On integration, we have integration of di, which is I, is equal to V0 by L constant out, integration sine omega t into dt. So now on integrating, I get I is equal to V0 by L, sine omega t into dt can be integrated as minus cos omega t divided by omega, because this is a function with respect to t, so it is divided by omega. Now, on equating this, I have I is equal to V0 by L. I'll just take this omega with this L, omega L. I is equal to V0 divided by omega L is the value, and since I know that cos theta can also be written in terms of trigonometric function for allied angles as sine pi by 2 minus theta. Since my theta is nothing but cos omega t and it is minus cos omega t, so I can write this as sine, that is minus sine pi by 2, and theta is minus omega t. Minus and minus plus, so that I can just change sine omega t at the first and then minus pi by 2 next. So I can write minus cos omega t equation in this way. So it will be sine within brackets omega t minus pi by 2 will be the equation. Okay, so this is sine omega t set of equation. Having this, we'll get to know that V0 omega L, V0 by omega L is nothing but I0 in this condition. That means to say that peak value, at certain peak value V0 by omega L, that means to say it is the peak value of the current, which can be written as I is equal to I0 sine omega t, but here we are subtracting minus 2, which means to say that the voltage value is considered as equation 1. Now let us consider the current value as equation 3, because we already have 2 over here. So refer for this voltage value and this voltage value, voltage V is equal to V0 sine omega t and current I is equal to I0 sine omega t minus pi by 2, which means to say that the difference between these two equations is minus pi by 2. That means to say the current is lagging when we compare with respect to the voltage. The current lags with respect to voltage. The current lags behind minus pi by 2, or the current lags 90 degree with respect to the voltage, or the voltage leads 90 degree with respect to the current. The leading is the voltage term and the lagging is the current term in this case. So what is that you give? How do you give a waveform diagram? So for this, waveform diagram is represented as, so this is a wave. So actually we start with respect to, this is omega t, which is phase, this is V or I. Y axis will be V or I. For that you start with your voltage. Your voltage comes out to be in this manner. So this is pi and this is 2 pi. Whereas your current is lagging with respect to minus pi by 2. If this term turns out to be 0 when t is 0, you are left out with minus pi by 2. So minus pi by 2 in the sense this part is pi by 2. So I can come with the diagram. Pi by 2, again this goes with center over here and again it comes center over here, it goes like this. So this is the phase difference. The current lags minus pi by 2, lagging is minus pi by 2 difference. This is the peak value of voltage, this is the peak value of current I0. Okay, so these are the terms. Dotted lines gives the current value and the solid line gives the voltage value, its peak value, and how exactly it is lagging. This is not in phase. The current lags behind 90 degree with respect to the voltage which is given. The current lags voltage or voltage leads the current. That is how it is you give. Next is phasor diagram, which is once again important. These two diagrams are important, for which you will have to write, this is phasor diagram. Here you have to have a y-axis, here you have to have an x-axis. So now when you give the diagram for this, one, that is the voltage, gives the positive axis which is said to be the omega t, it is the phase. But you know that the current lags by 90 degree, right? So this is the voltage, it is V0 and corresponding to it in the y-axis I give it as V. Okay, now this is the phase with an angle omega t. Now you have the current, what you have to give is negative axis of 90, negative. In order to have minus 90, you have to go down to this 90 degrees, so it will be like 90. So the complete thing is like pi by 2, it is in 90 degree. This angle is in 90 degree, so it is lagging 90 degree. The current lags 90 degree with respect to the voltage is what we study in this. So this diagram is very much important. So you need to know about the waveform as well as the phasor diagram. After this, we study about, that is the omega L. In order to know this omega L, this is called as a inductive reactance. Omega L is supposed to be called as inductive reactance, which means to say that omega L, inductive reactance, means X base L. This is the inductive reactance. We know omega is nothing but 2 pi nu into L, which is equal to XL. So this is the actual inductive reactance formula. So how exactly the inductive reactance work, which means to say that it is the opposition offered by inductance to alternating current, opposition offered by an inductor having certain inductance to the alternating current which is passing through it is called as a inductive reactance, which is given by XL, which is equal to omega L, which is equal to omega can be 2 pi by T into L, or it can also be called as 2 pi nu into L, where nu is said to be the frequency of it, which means to say that is inductive reactance is proportional to frequency, which means to say 2 pi L will be the constant things. So proportional means when the inductive reactance increases, you can see that the frequency also increases, is what we study in this inductive reactance. So suppose if in case of DC, in DC source, your frequency is nil, it is 0. When the frequency is nil, because it is not having that alternating cycles. So when the frequency is 0, you can see that your inductive reactance also said to be 0, which means to say there is no working of this inductors in case of the DC things, because DC does not have any of the effect from the inductor. This is what we study in case of inductive reactance. So in today's class, we have studied about the phasors and alternating voltage when applied to an inductor. What happens? That is, the current lags the voltage or the voltage leads the current. That lag and lead you will have to remember. Then we have drawn the waveform diagram as well as a phase diagram, and from that we have taken one component called as inductive reactance and given the inductive reactance formula as well as its relationship with the frequency and why exactly it does not have any effect towards the DC circuit. This is what we have studied today. Let us all meet in our next class with the upcoming sessions. Until then, have a good day. Thank you.